Imagine a world where quantum computing, with its potential to revolutionize technology, faces a significant hurdle: the fragility of quantum states. But what if there was a way to harness these delicate states in a manner that could unlock unprecedented computational power? That's exactly what a group of mathematicians and physicists in the United States has uncovered, potentially paving the way for robust, universal quantum computing. Quantum computers offer the tantalizing prospect of solving problems that are currently beyond the reach of classical computers. However, the quantum states these machines depend on are notoriously unstable. Topologically protected quantum states, which are more resilient to disturbances, have been seen as a promising solution. Yet the most viable methods for creating these states have a critical limitation. They restrict the types of computations that can be performed. Enter the concept of neglectons. A team led by Aaron Latta from the University of Southern California has discovered a method to overcome this limitation by leveraging a previously overlooked aspect of topological quantum field theory, TQFT. This breakthrough suggests that these quantum states might be far more versatile for computation than previously imagined. In topological quantum computing, qubits are represented by peculiar entities known as anyons. Unlike the familiar particles such as electrons and photons, anyons exhibit unique behaviors that make them ideal for quantum computing. Specifically, the state of anyons can only be changed by moving them around each other, a process known as braiding. This braiding alters the topological configuration of the anyons, which is crucial for performing quantum operations. However, not all anyons are equally useful. Some, due to their mathematical properties, seem to have no practical application in quantum computing. These are often dismissed as irrelevant. But Latta and his team saw potential where others saw dead ends. They realized that recent advancements in the mathematical tools for handling anyons could provide a new perspective. One of the key insights came from the work of Nathan Geer, Jonathan Kuyawa, and Bertrand Patchereau-Marand, who demonstrated that objects thought to be zero-dimensional in TQFT could actually be manipulated in novel ways. This opened the door to exploring the contributions of these previously dismissed anyons, which Latta's team dubbed neglectons. The inclusion of neglectons into the model allowed the team to perform a broader range of quantum computations. However, this approach introduced a significant challenge: the loss of a property known as unitarity. Unitarity is a fundamental requirement in quantum mechanics, ensuring that probabilities remain consistent. Without it, the results of quantum computations could become unreliable. To address this issue, Latta and his colleagues, particularly his PhD student Filippo Iulianelli, developed innovative techniques to confine the computational space to regions where unitarity is preserved. This breakthrough means that the full potential of topological quantum computing can be harnessed without compromising the integrity of the computations. Sean Kui, a researcher at Purdue University who specializes in TQFT and quantum computation, describes Latta's work as a major theoretical advance with significant implications for advancing the field. However, he notes that translating these theoretical findings into practical applications remains a long-term goal. Latta draws a parallel between the discovery of neglectons and historical instances where particles were predicted based on mathematical principles before being observed experimentally. He cites the prediction of the omega-minus baryon by Murray-Gell-Mann as a prime example. We already have systems where we're seeing Ising anyons, Latta explains. Now, we should also be looking for these neglectons in those settings. This research not only pushes the boundaries of theoretical physics, but also opens new avenues for practical quantum computing. As the field continues to evolve, the role of neglectons could be pivotal in making quantum computing more robust and universally applicable. What do you think about the potential of neglectons in quantum computing? Are you excited about the possibilities, or do you have concerns about the challenges ahead?